Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 5th lecture. In this lecture, we will be continuing with the overview of VLSI Design Flow. The topics that we will be covering in this lecture are RTL to GDS implementation. In particular, we will be looking into logic synthesis. In the earlier lectures, we have discussed that we can broadly divide the entire flow from taking the idea up to the final chip into 3 major parts. The first part is pre-RTL flow or system level design. The second part is RTL to GDS flow that we will be looking into today, and the third part is related to fabrication, and we call it as post-GDS flow. In the previous lectures, we have looked into the pre-RTL flow, and we have discussed that at the end of the pre-RTL flow, we get an RTL either through behavioral synthesis or reusing existing RTL, or maybe doing manual coding. So, at the end of the system level design, we will get an RTL for our design. Now, we want that to take that RTL up to the GDS or up to the final layout, and that part of the flow is known as RTL to GDS flow. Now, RTL to GDS flow is a very complicated design process, and we can divide it broadly into 2 categories. The first one is logic synthesis and the second one is physical design. So, the logic synthesis deals with taking an RTL and generating a netlist out of it. Netlist meaning the connection of logic gates. And the second part, the physical design, is basically taking that logical netlist and taking it into the physical domain or making a layout of it. So, in today's lecture, we will be looking into the logic synthesis part, and in the next lecture, we will be looking into the physical design. So, let us first understand what is logic synthesis. So, logic synthesis is the process by which an RTL is converted to an equivalent circuit in terms of interconnections of logic gates, and these logic gates are picked from the technology libraries that we give to the tool. So, let us look into the framework of logic synthesis, or what are the inputs and outputs of logic synthesis. So, the inputs or the major inputs that we give to the logic synthesis tool are, the first one is the design or the RTL that we want to implement. This design can be either in form of Verilog or VSDL, that is in hardware description languages, or it can be a combination of Verilog or VSDL format. The second major input is the library. Library contains the information of the standard cells that we will be using in our design. So, typically this library is in Liberty format, or the file that we use for library, those files have an extension of .lib. The third input or third major input that we give to the logic synthesis tool is the constraints file or constraints. Now, constraints contain the design goals, for example, the expected timing behavior in terms of maximum operable frequency, and the environment, meaning that what kinds of signal come into our design, what are the characteristics of those incoming signal in terms of their rise time, fall time, and so on, and what we expect of the signals that will be generated by a given circuit or the final netlist. So, those are defined in a file or a group of files which are known as constraints file, and typically we define the constraints in an format which is known as synopsis design constraint or SDC file. So, typically the extension of these files are .sdc. So taking these three kinds of inputs, the logic synthesis tool, what it does is that it generates a netlist. Now what is a netlist? Netlist is basically interconnection of logic gates. So from the last lecture we can remember that the RTL is basically the description of a design in terms of how signals move from one register to the another register inside our circuit. Now netlist is basically a interconnection of logic gates which is implementing the same functionality in terms of gates which are given or which are present in the library files, right. So the functionally the RTL that we give and the netlist both are equivalent, right. So functionally these two must be equivalent. One is a description of the design in terms of how the signals move between registers, and the netlist is basically interconnection of logic gates. The logic gates may be combinational logic gates, it can be flip-flops, it can be latches and complicated gates also, right. So the netlist that is finally generated by the synthesis tool, we can represent it in terms of Verilog constructs, or we can also see it in a schematic if the design is small and so on, right. So the interconnection of logic gates, those can be represented in various ways. Typically the Verilog constructs are used, and finally the netlist that is generated, that will also be in the form of .v or Verilog file. Now let us look into that what is an RTL and how what it is converted to, or its equivalent netlist. So in this slide I am showing an RTL, an example of an RTL or a modeling of a circuit in terms of Verilog, right. So we have not discussed the construct of or the constructs of Verilog language. So if you are not able to follow all of them, it is still okay, because we will be covering in later lectures the constructs of Verilog in more detail. So, but a few points can easily be noticed from this Verilog description of a design, that the design contains the input ports A, B, clock and select, and there is an output port which is named as out, right. And there is a wire which we call as Y, and this Y gets a value of B, else if the select is 1, else it is given a value of A, right. So this is somewhat a kind of construct which is describing a multiplexer, right. And then there is a code which is saying always at the rate of possess clock, something out is basically assigned a value of Y. So this is a kind of description of a flip-flop, okay. So given this description to the synthesis tool, it will translate it into a netlist, and the netlist will look something like this, right. For the first construct, it will generate a kind of multiplexer, and for the second construct, it will generate a flip-flop and connect them as per whatever is given in this Verilog file for the design. Then the same netlist can be represented in terms of this one is a schematic representation, we can say. And this is a netlist represented in Verilog using Verilog constructs, right. So the tool can synthesis tool can generate either of it based on what option we give to the tool. So both are basically representing the same thing. For example, here we have a multiplexer, so we in the Verilog netlist file will have a multiplexer, then we have a flip-flop, and we'll have a flip-flop in the Verilog file also. So both this schematic and the Verilog or netlist in terms of Verilog represent the same thing, right. Now let us look into the result of synthesis from the input output perspective, that what the output generated by the tool, or the netlist generated by the tool, how it was basically impacted by the inputs that we give to it, right. So suppose we have given the input the RTL we have already seen in the previous slide, right. I am not shown here just for brevity, and then the input that we need to give is the library, right. So library which must contain some cells which will be used in the netlist. So for example, the netlist that was generated in this case had this multiplexer and a D flip-flop. And from where does this multiplexer and D flip-flop come from? These were basically instantiated, or they were picked from these libraries and put inside our netlist, right, by the synthesis tool. So synthesis tool basically picks cells from the given library and based on some optimization criteria. And what optimization criteria to use and so on, those are defined by these constraints, right. For example, if we give a very relaxed timing constraints, then the tool will probably try to minimize the area, and in that case, if there are multiple multiplexers, there are more than one multiplexer in our library, then probably the synthesis tool, logic synthesis tool, will pick the multiplexer which has got the minimum area, because in the timing is not that much critical. So the performance can be traded off and area can be minimized in that case. So the constraints is basically defining our design goals or conveying our design goals to the logic synthesis tool. Now the translation of this, the translation of the logic of the RTL to the corresponding netlist, that is not that very difficult if the construct of the language, that is the Verilog language in this case, is well understood by the tool, right. So translating a Verilog construct or the hardware description language construct to a corresponding gate or logic circuit, that is not that difficult. The difficult part or the challenging part in the logic synthesis is basically how to do the optimization, right. And what we mean by this optimization is that how to pick the cells from the libraries and how to connect them so that the function of this RTL function or functionality in terms of logic and of this netlist both are equivalent, and while ensuring the equivalence, functional equivalence, how it can minimize the cost in terms of PPA, right. So if we want to minimize the area or the power or maximize the performance, based on it, the synthesis tool needs to pick the cells from this library appropriately, and this is a challenging task. So we will be looking at this challenge in more detail in later part of this course. But for now, just understand that what is the challenge in logic synthesis, because it will help us understand many other things or link together other tasks with logic synthesis tasks. Now, before going further, it is important to be familiar with some terminologies that are related to a design or netlist, or design which is in the abstraction level of netlist. Why we want to know these terminologies, or why should we be familiar with these terminologies? The first reason is that in the later part of this course or in the subsequent lectures, when we discuss concepts, we will be using these terminologies very heavily, and therefore if you do not if you are not familiar with these terms, then it will be difficult to follow the subsequent lectures. And the second reason is that the tools that we use in VLSI design flow, those tools also follow the same terminologies, right? So, if we want to give inputs to the tool, we have to give inputs in terms of these terms or these definitions that I will be describing in the subsequent slides. So, the first definition is what is a design? What is a design? So, suppose we have a netlist. This is a netlist, a design which is represented in terms of netlist, and this is the corresponding library. So, this is the library and this is the netlist that is generated by the tool, or we have got it from somewhere. Now, in this, what is a design? Design is basically the top level entity that represents the circuit. Now, in this case, the top level entity is this entire circuit, right? And we give name to it, right? So, the name that is given here is, say, my design. So, the name of this design that we are, or this circuit, will be my design, right? So, when we represent a netlist in terms of Verilog construct, then the design will be basically the top level module of the netlist. Now, the design actually takes input from the environment or external source or external world, and it produces some output, right? So, the interfaces of the design through which the design communicates with the external world, those interfaces are known as ports. So, the interfaces of the design are known as ports. For example, in this circuit, in1, in2, clock, out1 and out2. These are the interfaces through which the design communicates with the external world, and these are known as the ports. And we can classify the ports in terms of direction, and we can call the ports through which the signal goes inside the design. So, the signal goes inside the design, those are known as input ports, right? Those are known as input ports. And the ports through which the signals go outside the design, those are known as the output ports. So, in1, in2 and clock are the input ports, so because the signal goes inside the design through these ports, while the out1 and out2 are output ports because signals leave from the design for the and goes to the external world through these ports. So, these input ports are also known as primary inputs or PIs in short. And similarly, output ports are also known as primary outputs or POs in short. Then let us focus our attention on the library. Now, inside the libraries, the basic entity which delivers the combinational or sequential function, those are known as cells. So, inside these libraries, you will have, say, cells. These are the example of cells, and these cells will have some name. For example, here the name of the cell is A and 2, the name of the cell is NOT, and name of the cell is buff, and the name of the cell is DFF. So, these are the cells in the library. So, a design is basically a composition of multiple cells. So, we pick cells from the library and put it inside our design, right. So, multiple cells will be put inside our design multiple times, and those will be connected together, and we get the required functionality. Now, let us look into a term which is known as instance. What is an instance? So, instances are cells when used inside a design, right? So, when AN2 was a cell inside inside our library, right? Now, this AN2 cell was instantiated or put inside our design by the logic synthesis tool. So, when we put a cell into our design, the process is known as instantiation. The process is called instantiation, and while instantiating, the tool can give arbitrary names to the instances. For example, here I1 is the name of this instance, I2 is the name of the another instance, I3, out2 reg and out1 reg. So, these are the names of the instances. So, a point to note here is that the same cell can be instantiated multiple times, right. So, in this case, we can notice that the cell DFF is instantiated here also as well as here also. So, the same cell can be instantiated as many times as logic synthesis tool wants to instantiate, but the names of those instances will be different, right. So, in one case it is out1 underscore reg and in other case it is out2 underscore reg. Now, let us look at what are pins. So, pin is an interface, it is an interface either of a library cell, okay, or it is an interface of an instance. Both of them are the interfaces of both library cell as well as instances are known as pins, okay. So, it is an interface through which a library cell or an instance communicates with the other components in a design, okay. So, so in this design, what are the pins, right? So, the pins for this cell is AN2, right, are pin A, B and Y. For example, if we assume that this cell AN2 is a basically 2 input AND gate, then you will we can think of it as A and B are input pins of this cell and Y is an output pin of this cell. Similarly, if AN2 is instantiated, AN2 is instantiated inside our design, then it will have similar pins here A, B and Y, right. Now, the library pin and instance we can if we want to be more explicit, right, meaning that whether it is a pin of a cell or whether it is a pin of an instance, then we can use the term library pin to signify that it is a pin of a cell, or instance pin to specify that it is a pin of an instance, right, if you want to be explicit. But most of the time, based on the context, it is clear that whether we are talking about a library pin or an instance pin. If it is ambiguous, then we can use this term library pin or instance pin. Another point to note is that the direction of these pins can be either input or output, or in some cases it can be in out also, though it is not shown in this design. Some cases it can be in out also. For example, typically for IO cells, there the pins can be in out, where a same pin can work as an input pin or an output pin based on some condition or based on how the functionality of that pin is defined. Another thing to note about pin is their names, right. Now, if we look into the instances and the pin names, so multiple instances can have the same pin name. For example, if we look into this NOT gate, it has got a pin name Y, and A, right. Similarly, buffer, there is a buffer, the pin name is A and Y in the same for another instance also. Now, given a design, how do we uniquely say that which instance pin we are talking about, right? So, in that case, what we do is that we typically specify the name of a pin by a combination of instance name and a pin name, right, and separated by some separator. We can choose a separator as slash, right. In this course, for consistency, we'll always use slash to indicate that what is the pin name, right. But the separator between the pin name, the cell name or instance name and the pin name can be anything that is tool specific. Please be careful about it. For consistency, in this course, we'll always use this separator slash to specify the pin name. For example, if we want to talk about the pin A of this instance I1, right, this particular pin A, then we'll be talking, specifying it as I1, that is the name of the instance, then slash and then A, right. So, since the instance name is unique in a netlist, right, in a netlist the instance name cannot clash as per the Verilog construct, this kind of naming convention will always uniquely define a pin, right. Similarly, if we want to talk about the another pin B of I1, we will write as I1 slash B. If we want to talk about this Q pin and not about this Q pin, right, then we can write out1 underscore reg slash Q, right. If we want to talk about this one, then we will write out2 underscore reg slash Q, right. So, this is how you can uniquely define pin names. Now, let us look into what is a net in a design. So, net are basically the wire that connects different instances and ports in a design. Those are known as nets. So, in this case, this is net, this wire N1, N2, then this one is a wire, right, and so N1, N2, N3 till N8. These are the wires. These are the wires in our design, right. Now, one point to note is that typically the name of the nets that are chosen for the nets that are connected directly to the port is typically the same as the port name. So, typically the tool will choose the name of N1 of this particular net and it will choose the name and put its name as in1 typically rather than N1, right. So, for the nets which are connected directly to the port names are typically chosen as the net name. Okay, this is another point that you should be noting. Now, having looked into the terminologies of netlist, now let us look into a little bit about what are the tasks or what are the steps that goes inside the synthesis tool while it is transforming an RTL to its corresponding netlist. So, this figure shows the steps that are done internally of given an RTL to the logic synthesis tool and what steps will be done by the logic synthesis tool to generate a final netlist, an optimized netlist in terms of standard shells, right. So, the first step that is done or the first task, major task that is done by the logic synthesis tool is basically RTL synthesis. So, what is RTL synthesis? RTL synthesis is the initial part of logic synthesis and it consists of basically it translates an RTL to a netlist of generic logic gates, right. So, it takes an RTL, right, and it translates the construct of the RTL, and for example, if it is the RTL is written in Verilog, then it understands the Verilog language and it translates it in terms of generic logic gates, right? Now, what are generic logic gates? So, generic logic gates have got a well-defined functionality or Boolean operation function, right? For example, there can be a generic logic gate for an inverter, for an AND gate, for NAND gate, XOR, multiplier, multiplexer, demultiplexer, and such kind of simple combinational elements, or it can be latches or flip-flop, which are sequential elements, right? So, generic logic gate will have a well-defined Boolean function, right? But the generic logic gate will not have a fixed transistor level implementation, okay. So, the generic logic gate is just defining the logic or Boolean function for a given circuit, right. For example, in this figure I am showing you a generic inverter. So, this generic inverter is taking a value of 0, producing 1, taking an input 1 and producing output 0. This is the function, logic function, right. But its internal transistor level details are not yet defined, right. The transistor level detail of the inverter is defined in the library cell, right. So, if we consider any standard cell which exists inside the technology library, right, there we have an inverter whose all the transistor level details are already defined, right. So, we should contrast or we should differentiate between a generic logic gate and a standard cell. The standard cell has got a well defined transistor level description, right, while a generic logic gate has got the function but does not contain the transistor level description, and therefore, the generic logic gate is a higher level abstraction level in that sense, right. And since the transistor level description of a generic logic gate does not exist, we cannot say anything about the area, delay or power attributes of a generic logic gate, right. But we can get those estimates for the standard cells very easily, because those information are contained in the technology libraries, right. So, in the RTL synthesis step, that is in the first part, what we do is that we translate an RTL construct in the given RTL design that we give an input to the logic synthesis tool. That gets translated in terms of generic logic gates and or inverter, buffer, and those kind of generic logic gates will be used while generating this netlist in terms of generic gates. So, major task in this RTL synthesis is translation of the Verilog constructs to the corresponding hardware, right. Other task involved in RTL synthesis is basically parsing of the RTL, elaboration or checking for the connectivity, whether those are proper or not. A few optimizations can also be done, for example, related to arithmetic operations and compiler based optimization like constant folding and so on. So, these things will be discussed in more detail when we discuss RTL synthesis in later part of the course. Then once we have got a netlist in terms of generic gates, what we do is that, or the logic synthesis tool does, is that it does an optimization of the logic gates, right. So, what does this logic optimization means? That it is basically trying to improve some PPA, right, and since the input that we have given at this stage is just in terms of generic gates, we cannot estimate timing, power and even area numbers very accurately, right. But we can estimate say area in terms of number of generic logic gates, and that can be used as an estimate for an area, right. So, the logic optimization is done at the level of or taking this netlist in terms of generic gates, and it finally delivers a netlist which is still in terms of generic gates, but it is optimized typically for area, because area can typically be estimated more correctly for generic logic gates than other measures like say timing or power, right. Now, what is this logic optimization step? So, it is similar to the step that probably you might have studied in your initial courses of digital circuits, where you are given a logic function Boolean function, and you are asked to minimize it using, say, Karnaugh map and so on, right? So when logic optimizations were done at in the course of digital circuits, the number of variables that were treated were, say, 4, or maximum, say, for the Karnaugh map you might have gone to 5 variables or so, right? But if the number of variables increases a lot, for example, it become 100. Now in that case, how to do the optimization, right? So in that case, the techniques that we are you might have studied in digital circuit course, those are not cannot be applied directly. Those are modified or enhanced and made more sophisticated to handle a larger number or bigger circuits, and at the end of logic optimization we get a kind of a minimized logic circuit, right? But note that it is still in terms of after logic optimization we have still a netlist in terms of generic gates. Now once the optimization has been done, then a step is done which is carried out, which is known as technology mapping, right? Now in technology mapping, what is done is that the generic gates that we had, those are basically translated, or for them appropriate standard cells from the libraries are picked and put in the netlist. So technology mapping maps the netlist consisting of generic logic gates to standard cells in the given technology library. So at the end of this process, we'll get a netlist consisting of standard cells. Now this is not a very easy task, or it is a kind of challenging task, because if we consider, say, a generic gate in terms of inverter, right? Now in the library, in the technology library, we'll have a multiple implementation of an inverter, right? For example, of size 1, 2, 4, 8, 16 or so on. The size of the, I mean to say, the size of the inverters, right? So the typically when we make a technology library, in that for the same logic function, in this case an inverter, we have multiple cells of different drive strength, right? If we increase the area, typically the drive strength goes on increasing, but the area cost also goes on increasing, right? Why we design multiple types of inverter or inverters with multiple drive strength in a library? The reason is that then it gives the flexibility to the logic synthesis tool to pick the one which is appropriate. For example, if an inverter is coming in a very timing critical path, then it will use an inverter of, say, higher drive strength, so that the timing improves, delay decreases. And if the inverter is not that much critical on the timing path, then probably it can use an inverter with the lowest drive strength and the smallest area, right? So there is a lot of flexibility there are many options available for a logic synthesis tool to do a mapping of a generic netlist in a generic in terms of generic logic gates to a netlist in terms of standard cells, right? Because there is, for the same function, it can be covered in many different ways using standard cells, and using the same cell or same function, we can or for the same Boolean function, we can pick many different kinds of standard cells from the technology library. So the solution space is huge, and to find an optimum solution from that solution space is a challenge that the technology mapper needs to handle. Then once once the technology mapping is done, then we get a netlist which is in terms of standard cells, right? Now we say that the standard cells have got the transistor level description very well defined, right? It has got the transistor level meaning that using the standard cells information in the technology library, we can basically derive many estimates more accurately. For example, we can estimate what will be the delay of an inverter, because in the technology library, there is an information regarding what will be the delay of an inverter under what condition, right? From that information, the delay can be derived, and for the whole circuit, a kind of delay calculation can be done and timing estimates can be made. Similarly, power estimates can be made. Also, once we have committed to a standard cell, we can estimate the area and so on, right? So, once we have got a mapped library or technology mapped, mapped design or technology mapped netlist, then over that we can do optimization more accurately, because PPA estimates can be made much more accurately. So, after the technology optimization step, technology mapping step, a step is done which is known as technology dependent optimization for timing, for power, for area, right. Now, once this optimization is done, then we have got a standard, we have got a netlist implemented in terms of standard cell, and also it is optimized. Now, this netlist can go to the next step, which is basically the physical design step. There are a few more steps in between related to design for test, but those things we'll be discussing in more detail later in the later part of the course. But for now, we can consider that once we have done the logic synthesis, we have got a netlist, and that netlist can be passed to the physical design for the further processing, right. So, these are some of the important references that I have used in this lecture, and you may refer to them for more understanding. So, in summary, what we can say that in this lecture, we have looked into the RTL to GDS flow, the RTL to GDS implementation flow, and in that we have looked into the logic synthesis part, and at the end of the logic synthesis, we have got a netlist. We get a netlist which is implemented in terms of standard cells, and then we can take that netlist and carry out the next part of the RTL to GDS implementation, that is physical design. So, we will be discussing physical design in the next lecture. Thank you very much.